Okay, so here's a second video, just a different scenario really. Just to touch on a couple extra things. So here we have resistor 17 ohms, 90 volts, 60 hertz. So just be aware, I can change when in our handouts. There's different values. Not everything's 120. We got 90 volts here, 17 ohms, 9 ohms. So we just have a different shape right here. The algebra stays the same values, so we square root 19.2 at an angle of 27.8, and again, this value should always be present. Punch it into our vectors, or in polar form, and this is what we have. So I just wanted to mention here, whenever we have values and you got amps, take it to 2 decimal places, 3 if you like. But it'll help when we get into our volt amps there. So I just wanted to make mention of that. Take the amps, the more decimals you carry, the better off. But 2 decimals sort of makes it work. So here we end up with 4.68 amps. We go through this process here. Again, so iTotal, I used iTotal for this one. But again, I through R and I through L is just more specific. We get 90 volts. Polar, again, this is a good exercise. We're going to be doing lots of that. And that ties into our vector exercises. So here again, the volt amp. So you got 421.2 volt amps. Use our algebra, true power. And just get used to this terminology, true power, reactive power. It's all part of the language, and that's what a lot of this is about. It's about introducing the formulas and the language. So where our points are sitting is in the formulas. You're going to have to express these formulas. The values, the polar is not part of what's going to be on a test. For example, this is just all in preparation, and it's a nice way to sort of double check everything. So all we're really focused on is the formulas themselves and the calculation, but this is about an introduction to the language and the system of solving these kinds of circuits. So 4.68 amps, 90 volts, so we have the polar, and remember that this is unlike a regular series circuit where these voltages will not add up to the source voltage. So here we got, for example, 421.2 gives us our true power here, 372, 197 for the VARs. So here we end up with a bit of just a slightly different value, and that's what I mean about carrying the decimals over, matching the VA to the calculated value here. So and then right here we stick in polar, you end up with something just a little bit different again. So I just wanted to make mention of those kind of values, so you'll have slight variances depending on how you use your calculator really. Power factor, again, we're looking at the cos relationship. So you have adjacent, hypotenuse. So out of the SOHCAHTOA, we're looking at the Ka, I suppose. So ER, ET, R to Z, P to VA, same thing, 88%. Now we're looking better than the previous. Now when it comes into which VA value to use, which volt amps, we got this one, it doesn't really matter to me. We can pick one, go with it. And again, you can use anything you like. You can use your voltage, you can use your resistance, but I just go with P and VA because it's the last one in the calculation. And then we calculate for our inductance of the coil, and we have the inductance is XL over 2 pi F. F being the frequency, 2 pi. Whenever we're dealing with pi, we're dealing with a circle. And when we're dealing with generating here the frequency, because the frequency here, 2 pi F, we're talking about the 90 volt the power source here. So the frequency is relative to your power source. So the frequency here is 60 hertz, so 2 pi times 60 gives us the 376.9, so we end up with 0.02 henries, and that's the inductance of the coil right here. So that was just a couple of extra things added in there, and that's it for that video.